The trickiest part of Roman numerals is not the addition. It is one counterintuitive subtraction rule, where a smaller symbol before a larger one is subtracted instead of added. Today, let's look at Roman to integer.
Opening.
We are given a string of Roman symbols and must convert it into its integer value. The Romans used 7 symbols. I is 1, V is 5, X is 10, L is 50, C is 100, D is 500, and M is 1000. Normally, the symbols run from largest to smallest, and we simply add their values. But there's a twist. When a smaller symbol appears immediately before a larger one, that smaller symbol is subtracted instead of added. There are exactly 6 subtractive pairs. I before V or X makes 4 or 9. X before L or C makes 40 or 90. And C before D or M makes 400 or 900. Our job is to walk through the string and decide at each symbol whether to add or subtract it. Core idea. The key insight is that we can make the add or subtract decision locally, just by comparing each symbol with the one that follows it. We scan the string once from left to right. At every position, we look at the current symbol and the next symbol. If the current value is smaller than the next value, we are standing on the front half of a subtractive pair. So we subtract the current value now. Otherwise, we add the current value. The reason this works is beautifully simple. By subtracting the smaller symbol early, we set up a discount that is more than recovered when the larger next symbol is added on the very end. Next step. So, a single left to right pass, comparing each symbol only with its neighbor, produces the correct total without ever needing to look back or to store pairs. Key details. A few details keep the scan correct. First, we predefine a lookup from each of the 7 symbols to its integer value, so any value is found in constant time. Second, we keep a running total that starts at 0 and is updated at every step. Third, the comparison only happens when a next symbol actually exists. The very last symbol in the string has no follower, so it is always added, never subtracted. Fourth, the decision uses a strict less than comparison. If the current value equals the next value, that is a normal addition. Because Roman numerals never place a symbol before an equal one to signal subtraction. Fifth, subtractive pairs are always exactly 2 symbols long, so a one-step lookup is enough. We never need to look 2 symbols ahead. Walkthrough. Let's trace the example spelled MCMXCIV print, a 7-symbol string that should evaluate to 1994. This example is rich because it contains all 3 kinds of subtractive pair. CM meaning 900, XC meaning 90, and IV meaning 4. We enter the function. Our first job is to build the lookup mapping each Roman symbol to its integer value. I maps to 1, V to 5, X to 10, L to 50, C to 100, D to 500, and M to 1000. Every step of the scan will consult this lookup. Now we initialize the running total to 0 and record that the string length is 7. Knowing the length lets us detect the last symbol, which has no next symbol to compare against. We move to the first symbol at position 0. It is M, worth 1000. We compare it with the next symbol, C, worth 100. 1000 is not smaller than 100, so this is a normal addition. We add 1000, and the total rises from 0 to 1000. We move to position 1. The current symbol is C, worth 100. The next symbol is M, worth 1000. 100 is smaller than 1000, so this is a subtractive pair. The C is the front half of CM, meaning 900, so we must subtract the C now. We subtract 100, and the total drops from 1000 to 900. This temporary dip is exactly the discount we spoke about. It will be more than recovered when the larger M is added on the next step. We move to position 2. The current symbol is M, worth 1000. The next symbol is X, worth 10. 1000 is not smaller than 10, so this is a normal addition. We add 1000, and the total rises from 900 to 1,900. Notice how the earlier subtraction of 100 and this addition of 1,000 together yield a net 900, which is exactly the value of the pairs CM. We move to position 3. The current symbol is X, worth 10. The next symbol is C, worth 100. 10 is smaller than 100, so this is another subtractive pair. The X is the front half of XC, meaning 90, so we subtract the X now. We subtract 10, and the total drops from 1,900 to 1,890. Again, this discount will be recovered when the larger C is added next. We move to position 4. The current symbol is C, worth 100. The next symbol is I, worth 1. 100 is not smaller than 1, so this is a normal addition. We add 100, and the total rises from 1,890 to 1,910. Here too, the earlier subtraction of 10 and this addition of 100, net to 90. The value of the pair XC. We move to position 5. The current symbol is I, worth 1. The next symbol is V, worth 5. 1 is smaller than 5. So this is the third subtractive pair. The I is the front half of IV, meaning 4. So we subtract the I now. We subtract 1, and the total dips from 1,990 to 1,908. Why 9? This final discount will be recovered when the larger V is added next. We move to position 6. The last symbol, it is V, worth 5. There is no next symbol, since we have reached the end of the 7-symbol string. So this is a normal addition. We add 5, and the total rises from 1,989 to 1,994. The last subtraction of 1, and this addition of 5 net to 4, the value of the pair IV. The scan is complete. Every symbol has been visited exactly once, and the running total is 1,994, which we hand back as the final answer. Notice the rhythm of the trace. The 3 subtractive pairs, CM, XC, and IV, each showed the same pattern. A smaller symbol was subtracted on one step, and the larger follower was added on the next step. Netting to the correct pair value, every other symbol was simply added. The whole computation was a single left-to-right pass with only a 1-symbol lockept, and no pair was ever stored explicitly. Complexity. The running time is linear in the length of the string. We visit each symbol exactly once, and at each step we do a constant amount of work, 1 lookup, 1 comparison, and 1 update. The extra space we use is constant. Because the lookup holds a fixed 7 entries, and we keep only a running total and a couple of end ICEs regardless of how long the input string is. Summary. Roman to integer comes down to a single rule applied at every symbol. The ideas to remember are these. Build a lookup from each symbol to its value. Scan from left to right, comparing each symbol with its immediate neighbor. If the current value is smaller than the next value, subtract it now. Otherwise, add it. The last symbol always has no follower, so it is always added. Subtracting the smaller symbol early is recovered with profit. When the larger next symbol is added, thank you all, and see you next time.